Hey guys, before we continue, I just wanted to follow up on the previous video. I forgot to answer the second part of the question where it asks to find the x and y intercepts, but luckily we already did that along the way if you look back at our old questions. So let me just walk you through that. Remember, for the x-intercepts, we're looking for where y is equal to 0. So that'll be here and here, right? You got -4 comma 0 and 4 comma 0. And then the y-intercept is when x is 0. So the y-intercept would be 0 comma 4. That's for problem number 1. Problem number 2, same idea. You got these intercepts here, right? First, the x-intercepts. That's when y is 0. So that's -7 comma 0. And then the y-intercepts when x is 0, 0 comma 7 and 0 comma -7. These guys right there. Okay, and then for number 3, there's only one intercept, and it's actually both because it's 0, 0. It passes through the x-axis and the y-axis. So anytime you have an intercept at the origin, it's both the x-intercept and the y-intercept. Same thing applies for number 4 as well as for number 5. And you can see how many times I tried to re-record this and fix it because you see all the different colored dots right there in the center. I couldn't erase because it's all attached to the other one. Okay, so anyways, let's continue. So number 3, 4, 5, same thing, all at the origin. Number 6, the x-intercept is when y is 0. So that's right here and right there. You've got it at -1 comma 0 and 1 comma 0. And then the y-intercepts are these guys. That's when x is 0. So 0 comma -1 and 0 comma 1. All right, let's get back to our main notes. And I made a small update, but the one that you guys see in our Lamaku site is the most updated version. So yeah, there it is. Okay, number 3. Find the symmetries in a graph. So there's 3 types of symmetries. There's first of all y-axis symmetry, and then there's x-axis symmetry, and then there's origin symmetry. So for y-axis symmetry, this is like you might have expected. It's symmetry across the y-axis. So let's draw a quick picture here. And the standard, oops, that's crooked. The standard example I give for y-axis symmetry is this one function, one of our very favorite functions. Here's x-axis, y-axis, and that is y is equal to x squared. So our good old friend, the parabola, right? Something like that. And what do you notice about this? Well, it's symmetric about the y-axis because if I was to flip this over the y-axis, it would land right back on top of itself. And one other thing to notice is that this power is even, right? And it turns out anytime you have an even powered function, it has this kind of symmetry. And for that reason, we associate the two. And that means vice versa. If I have a function that has this kind of symmetry over the y-axis, I'm going to call it even. And if I have an even function, like with the terms of the powers, then it's going to have that kind of y-axis symmetry. Now, this also works not only for x squared, but what if this was x to the 4th or x to the 6th? Any of those would still work. And in fact, you can even do combinations of different even powers, like x to the 4th plus 3x to the 6th minus x squared. And as long as these powers are all even, then it's going to have this kind of y-axis symmetry. So nice little side fact, where we get the intuitive idea for calling y-axis symmetry functions even. Okay, next type of symmetry is x-axis symmetry. And the standard example that I think of usually for this one is pretty much that same example. Oops. Same example I just gave you, but we're going to just flip it. Because what is x-axis symmetry? It's going to be symmetry over this x-axis, right? If I flip the function over that way. So here, how about we just do x equal to y squared instead? Now that picture looks something like this, like a parabola that's on its side. Technically, it's not a function because it doesn't pass the vertical line test, but it is still an equation you can draw. And if I flip this thing over, the x-axis lands back on itself. So it's got x-axis symmetry. Now, when you're trying to check for these two types of symmetries, what you're looking for is if it has x-axis symmetry, you flip the x with a negative x and see if the equation is unchanged. And if it's unchanged, lands back on itself, then it's got x. It's got y-axis symmetry. So note that it's kind of opposite, right? To check for y-axis symmetry, I'm changing the x with negative x. And same thing applies for the other way for x-axis symmetry. So if I want to check for x-axis symmetry, then I replace y with negative y and see if that equation is unchanged. Now, one more type of symmetry, which is the origin symmetry. This is symmetry across the origin. And what that really means is if I take my graph and I flip it twice over the x-axis and then across the y-axis, then it gives me back to where I started. Or another way to think about that is if I was to take my function and just rotate it 180 degrees, am I going to land back on myself? Now, the standard example I think of for this one is y is equal to x cubed, which another one of our favorite friends, right? It looks something like this. And think about what would happen if I was to rotate this guy 180 degrees. Well, this part would land back in itself over here. So like what I mean is like this red part, if I was to rotate 180 degrees, that would end up over here, right? So that would be this new red part. And then meanwhile, this black part, well, actually black is not a good choice because black is the color of my axes. Let's use orange. This orange part, if I was to rotate 180 degrees, that would land on itself right there. So then you end up back with the same thing visually, right? Now, how do you check algebraically? Sorry, I forgot to label these axes. How do I check algebraically if I have an odd function? Well, the way to check is you actually replace both the x with a negative x and the y with a negative y. And then you see if the equation is unchanged. You may have also seen this slightly different version where if you say, okay, if I plug in x and then I plug in negative x, it's the same except with a negative. That's another way to think of odd functions. All right, so that's the gist of those three symmetries. The big thing that you need to know to check are these procedures that I have highlighted in pink. Let's try problem 7 through 11 now. 7 through 11, one at a time. Okay, so let's copy and paste these things. My notes don't like me to start a new page unless I have drawn to the bottom for some reason of my previous page. Okay, so starting with number 7 first. Let's do number 7 first. Okay, sorry guys. There, let me just do this one at a time. Oh, stop that. Actually, let me just copy from the original here. Sorry guys to make you watch me fumble around with this thing. Okay, here we go. So 3 types of symmetries we're gonna check, right? And this is what we're gonna do each time. So we'll check let's check them in the order that I introduced them, which was okay, we did y-axis symmetry first. The y-axis. My pen is too thick. So to check y-axis symmetry, we replace x with negative x and see what happens. So let's write it like this. Y of negative x is going to be negative x squared plus 2 over negative x to the 6th. And then anytime you take an even power of something, we just get back itself, right? So it's going to be x squared plus 2. And then this is going to be 5x to the 6th. So comparing this with our original, it's the same. So yes, we have y-axis symmetry. Okay. What about x-axis symmetry? So for that one, we're going to replace y with negative y. Okay, so this is negative y equals to x squared plus 2 over 5x to the 6. And then we want to, reduce it back to get y by itself again so we can compare. If I do that, I'm going to get y is equal to negative x squared plus 2 over 5x to the 6. And now this thing is not quite the same as the original because now I have a negative sign, right? So no, not symmetric across the x-axis. Okay, so lastly, we check both. So does it have, origin symmetry. Okay, and the way we check that is we replace y with negative y, and we replace x with negative x, and then we see what happens. Okay, well, I'm going to have negative y is equal to this one. When I square it, it's going to give me x squared plus 2 over, this is going to be 5x to the 6. But I still got this negative y to deal with, so divide by negative 1 on both sides, I get y equal to negative x squared plus 2 over 5x to the 6. So that is not the same as the original, so no, I don't have origin symmetry. That was number 7. And this same procedure, we're just going to repeat this for all the questions. So your guys' job, try out each one by one. We have a total of 5 of these to do. All right, let's do it. So same thing, do y-axis first. We're going to replace x with negative x. It's going to be negative x to the third minus negative x. So that's going to be negative x to the third is going to be negative x cubed because 3 negatives makes a negative, right? Then I have minus the negative, that's going to be plus x. So I have negative x cubed plus x. That's not the same, right? So no y-axis symmetry. What color did it look like? Next is x-axis symmetry. But without even completing this, I know it's going to have x-axis symmetry. I'm sorry, no. I'm sorry, I take that back. I know it's going to have origin symmetry because that's an odd function, right? Look, there's odd powers. Okay, so I'm giving away the answer. Let's just work through it. So next I'm going to replace y with negative y to check x-axis symmetry, right? So but then I want this to resemble this, so I got to get y by itself, divide both sides by negative 1. I'm going to get y is equal to, and take that negative 1, apply it to everything on the right-hand side of the equation. So I've got y equals to negative x cubed. The negative distributes to that negative there, negative x cubed plus x. Now this does not look like the original, so no x-axis symmetry. Okay, what about origin symmetry? This is the one I know it should have because it's an odd function, right? So let's replace y with negative y and x with negative x. And be careful here with the parentheses. My recommendation is to replace the whole thing with negative x in parentheses so you keep all your signs straight. Okay, working this out, I got negative y, negative x to the cubed is going to be negative x cubed. Negative because there's 3. Negative is going to be positive. Like that. And now I have to deal with this negative. Let's multiply both sides by negative 1. So I'm going to get y is equal to, this part switches to a x cubed. This switches to a minus x. So x cubed minus x. And oh, look, that's what I started with. So yes, symmetric across the origin. That's 2 down, 3 more to go. Okay, so here's number 9. Y-axis first. Okay, there's a couple of ways that you could approach this question. I think personally, it's easier if I just expand this first. So before I even check my symmetries, I'm going to actually just expand this. X minus 1 squared. That's x minus 1 times x minus 1. Gives me x squared minus 2x plus 1. And if you're not sure where that came from, just write it out and FOIL it, right? First, outer, inner, and last. And then you'll end up with this form. This is one of those ones that you kind of want to just remember though. It's double this part with an x, and then this last part ends up squared. It's one of those usual forms. Okay, let's check y-axis symmetry. So we're going to replace x here with negative x. So I'm going to have y is equal to negative x squared minus 2 negative x plus 1. Negative x squared is just x squared. Minus 2 of negative x is a plus 2x. And then plus 1. So comparing this guy with that guy, not quite the same, right? Because one of them was negative, one of them was positive for that 2x portion. So nope. What about x-axis symmetry? Let's see. So this time I'm going to replace the y with a negative y. And then on the other side, I'm going to keep that the same as it was originally. Originally meaning this portion here. Now to get y by itself, multiply everything by negative 1. So it's going to be y is negative of all that stuff, right? And if I take negative of all that stuff, it's going to be negative x squared plus 2x minus 1. And that doesn't match up because I've got signs all backwards. So nope, no x-axis symmetry. My suspicion is that there's no symmetry here. Because I've got even and odd functions mixed up too, right? I got an even function and an odd function. X is just x to the 1. But we're going to check anyway. So we're going to place y with negative y. And this right-hand side of the equation with all the opposites. So negative x squared minus 2 times negative x plus 1. And then let's work this out. Negative y is equal to negative x squared is x squared. Minus 2 negative x is plus 2x plus 1. And then let's deal with this negative sign attached to everything. It's going to be y is equal to negative of all that stuff, which is y is equal to negative x squared minus 2x minus 1. Looking at this, does not match up there. So no symmetry whatsoever. Okay, 2 more to go. Number 10. Number 10 is looking to me right off the bat. My intuition is telling me probably not again. It's definitely not. Oh, actually, no, I take it back. Maybe we'll have x-axis symmetry. I don't know. Definitely not even because here's an even, here's an odd. Definitely not odd because here's an odd, here's an even. Only likely thing maybe is the x-axis symmetry. But we're going to check anyway. Y-axis first. We're replacing x with negative x. And this is 6 negative x cubed plus negative x. So it's going to be 10. Negative x squared is x squared. And negative x cubed is going to be negative 6x cubed. And then minus x. So no, doesn't match. So not y-axis symmetry. Next is x-axis symmetry. So we have negative y is equal to 10x squared over 6x cubed plus x. Then I want to get rid of this negative, so I'm going to switch it. It's going to be y is equal to negative 10x squared over 6x cubed plus x. Or the negative could just go in the front. And looking at that thing, no, it's not the same, right? Because here I have a negative at the top, here I don't. By the way, this negative sign, it could go at the top, the middle, or the bottom. It's all the same. If you put it in the bottom, though, make sure that you include parentheses around everything. Yeah, when you flip it, when you switch it to the other side, I mean. Okay, so nope. No axis symmetry either. And then, no origin. Let's check. So origin, I'm going to do both, right? I'm going to do negative y is equal to, and then replace all the x's with negative x's. Okay, so I have negative y is equal to 10x squared over negative 6x cubed minus x. Then what I'm going to do is I'm going to take this negative and transfer it to that side. So it's going to be y is equal to the negative. You know what I'm going to do, guys? I'm going to attach it to the bottom because I see some negatives on there on the bottom. So I'm a negative of negative 6x cubed minus x. Oh, and I see my intuition was actually wrong here, guys, because watch what happens. Watch what happens. So this is 10x squared on the top. Negative of negative 6x cubed is positive 6x cubed. Negative of negative x is positive x. So wonder of wonders. This matches up with my original. So it actually is odd. It is odd. And now that I think about it again, that does make sense, because if I take x squared divided by x cubed, that gives me an x on the bottom, right? And x squared on the top, x on the bottom, that gives me the x on the top. So actually they're both odd. It's like a equivalent of an odd function. Okay, anyways, turns out that is an odd function. I mean, yeah, an odd function, so it's symmetric about the origin. Sweet. All right, guys, one more. So that's why it's important to actually check, yeah? Sometimes our intuition is incorrect. Okay, number 11. X squared plus y squared equals to 36. Oh, okay. Well, you know, this is a form of a circle already. So this is a nice one because I can actually picture it in my head. Radius 6 circle. Oh, that does not look like a circle. I wonder if this thing will fix it for me. Yes, it does. Nice. So I have a circle. Oops, something like that. Looking at this thing, it's clearly got x-axis symmetry. I mean, that was y-axis symmetry. It's clearly got y-axis symmetry. If I rotate it, still symmetric. So it should have all I'm suspecting. Let's check anyway. Oh, yeah, I'm sorry. I've been doing y-axis first this whole time, yeah? Y-axis, sorry. Y-axis symmetry. Let's check. So to check, I'm going to plug in negative x. When I plug in negative x in a squared, I get x squared plus y squared. So same thing. Yes. Next is x-axis symmetry. So that's, to check that, I plug in negative y for y. Oops. And then when I square negative y, I end up with just y squared anyway. So that checks out the same. Yes. X-axis symmetry. And then you can already see what's going to happen with the origin, right? Negative x plus negative y. Squaring both. Squaring negative x, I get positive x squared. Squaring negative y, I get positive y squared. And that looks like the original. So check, yes. All three types of symmetry. Fantastic. Okay, guys. See ya in the next video. Hope this is making sense to you. If not, feel free always to reach out to me, schedule an appointment, or send me an email.